Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutiwa Sos Ugobela Maths. And without any further ado, let's look at this question that we have here. Okay, so we have question 6 still on chemical equilibrium. It says the reaction between steam, so steam is our water in gaseous form, and then chlorine gas reached equilibrium in a closed container according to the following balanced equation. So we can see our balanced equation and that all the substances that are involved here are in gaseous state. So that means all of this can be substituted into our Kc expression. Remember, in our Kc expression, we only put substances that are either in aqueous state or in gaseous state. So the solids and liquid, we do not put them there because their concentrations remain constant throughout the reaction. Okay, so we have 6.1. It says, is this reaction exothermic or endothermic? Give a reason for the answer. Now, looking at this part here, we can see that our enthalpy change is a positive value, so which obviously would suggest that our forward reaction is endothermic. So we are supposed to say endothermic, and the reason for that is because our enthalpy change is greater than 0. It's positive, right? So note that. And then, okay, 6.2 says the graphs below, not drawn to scale, show how the amount of product present in the container change with time at a specific temperature. The volume of the container is 5 dm cubed. Now, 6.2.1 says which reaction is favored. Choose from forward or reverse. Give a reason for the answer. Now, from looking at the graph, we can see that this graph, they say it indicates the amount of product with time. But then if the amount of product is decreasing with time, then we know this obviously means that the reverse reaction is favored. Because what is the reverse reaction? It is simply a reaction that promotes the using up of product in order to form back the reactants. So in a reaction, if we find the number of products or the amount of products decreasing, then this tells us that the reverse reaction is favored. But if we find the amount of products increasing, then this tells us that the forward reaction is the one that is being favored, right? So forward reaction is favored when products increase, and reverse reaction is favored when products decrease. So our answer for 6.2.1 here, it's supposed to be reverse. So 6.2 is reverse. And then again, what's the reason for that? So we say the amount of product decrease with time, right? So the amount of products decrease with time. And then we have 6.2.2. It says, how do the rate of the forward and the reverse reaction compare at time t3? At time t3, we can see that this is when the reaction has reached a point of chemical equilibrium, right? So we say at that point, because we can see that the concentration of your products have now reached a constant level there. So we say at that point, our reaction has reached chemical equilibrium. And if you were to remember the definition for chemical equilibrium, it says this is when the rate of the forward reaction is equal to the rate of the reverse reaction. Right. So obviously from spotting that definition, we are now able to say that at that point, the rate of the reverse reaction is equal to the rate of the forward reaction. Right. And then we have 6.2.3 says, calculate the equilibrium constant Kc for this reaction at the temperature. At this temperature, if there was initially 5 grams of water and 5 grams of chlorine, right? So what you needed to note with this question, similar to the question that I just uploaded recently, so the last one that I just uploaded, is the fact that here, the reverse reaction was favored, right? And then if the reverse reaction is favored, there are a couple of things that you need to know. Okay, so here are the things that you need to note. Here we have for our ratios. So if we can just write here, we have 2H2O and then followed by 2Cl2 and then to give us 4HCl and then plus O2. And then all of this are gases. Now on our ratio, we're just going to drop the coefficients. So we have 2 here and then we have 2 here and then we have 4. We have 1, right? So that's all you do on the ratio block. And then for the initial, we were given here, looking at this graph, remember, time t0 represents the initial, right? So what you need to note with this question that is different from the other question is the fact that initially here your products were not 0, right? So initially, so this is a part whereby this reaction is coming from a particular equilibrium. And then now starting to establish the new equilibrium, the initial number of moles would have to be the number of moles that were accumulated at the previous equilibrium. So that's what you need to note, which is similar to what I've just posted recently with that video where I told you that you have to note if this reaction is coming from a particular equilibrium and now it's trying to establish a new equilibrium, the product will not start at a concentration of 0. So you'll be given the concentration of the product to start with. So initially we can see that the product, our O2 is at 0.3 and then our HCl is at 1.0. These are the initial number of moles that you need to start with. So that means we have 0.3 here. And then here we have 1.0, right? And then reading further, we were told that initially there was 5 grams of water and 5 grams of chlorine, right? So that means to calculate for this ones, we can say, let's calculate the number of moles of water H2O. This would be mass over the molar mass. Then our mass is 5 grams, but then the molar mass, so let's just say 5. But then the molar mass of water, we know that's 2 plus 16 is supposed to be 18. And then if you punch it into your calculator, what do we get? That's 0.28 mole, right? So we're just going to go ahead and substitute it here, 0.28. Then again, we need to calculate the number of moles of the chlorine gas. So that's M over big M. So again, it's 5, but then over 71. Remember, chlorine is 35.5 from the periodic table. So if you say 35.5 multiplied by 2, that's where you get this 71. And then if you say 5 divided by 71, that's 0.07 mole rounded off to 2 decimal places. So we want to have it here, 0.07. Right. So now we have the initial number of moles for every substance that's involved there. But then, okay, how do we then continue? If you are to take a look here, we can see that at T3, remember we did say that at T3, this is the part where the chemical equation reaches what we call the chemical equilibrium. So at that point, we say that your reaction has reached a state of chemical equilibrium. And then at chemical equilibrium, we can see that the number of moles of O2 have now decreased to 0.1. So there's 0.1 mole at equilibrium for the oxygen. So we're going to put it where? Equilibrium number of moles. That's 0.1, right? And then what about the HCl? Now looking at HCl, we can see that if we can just draw a line, extrapolate like how they did it on oxygen here. So let's form an extrapolation line to see where it hits on our y-axis, and then we can see that this line there is in between the 0.1 and 0.3. So it's a midpoint between those 2 points, meaning that it has to be 0.2, right? So that means again here at equilibrium for HCl, we have 0.2. But then from this reaction here, another thing that you need to note is the fact that the reverse reaction is favored. Why? Because we can see that the concentration of the reactant will now be greater than the concentration of the product. Remember, from looking at this graph, we can see that the number or the amount of product is decreasing with time, right? So obviously this would have to suggest what? This is what you need to note. If reverse reaction is favored, then there are a couple of things that you need to note. For the reactant sides, if you are looking for the number of moles at equilibrium, you need to be able to say I plus C is equals to E. But then if you are looking for the products at equilibrium, then you need to note that right now you say I minus C is equals to E. So what does this mean? It means right now if the reverse reaction is favored, then you have to add on the reactant and subtract on the product, right? Because remember, the products are now being used up and the reactants are being formed, right? So at this point, we know that from 0.3 to 0.1, there was a decrease or a change in the number of moles of 0.2. And then again, from 1.0 to 0.2, there was a change in the number of moles of 0.8, right? Now, how do we find this 2 here? Obviously, we now need to use the ratios. So if we can use the ratio of oxygen gas here to the ratio of chlorine gas, we can see that the ratio is 1:2, meaning that we can simply say 0.2 multiplied by 2 divided by 1, right? So obviously, the ratio suggests that if we have 0.2 here, then on this one, we need to have twice the number of moles. So if this is 0.2, twice the number of moles is 0.4, right? And then looking at this one, again, it's the same scenario. And then even if you can look here, the ratios are the same. So that means they have to have the same number of moles on the change block. So 0.4. Always remember that the change block is the one that relates to the ratios. So the only block whereby you have to use the ratios is the change block here, right? Not in the initial, not in the equilibrium, only on the change block. And then now to find our number of moles at equilibrium, remember for the reactants, I need to say initial plus the change is equal to the number of moles at equilibrium. So that's 0.28 plus 0.4, which will give us 0.68. Then here we have 0.07 plus 0.4. This will give us 0.47, right? But then we are not done. Remember, we do not calculate the Kc using number of moles. We calculate Kc using the concentrations. So how do we then find the concentrations? Remember, reading here, we are told the volume of the container is 5 dm cubed. So if you want the concentration, it's the number of moles at equilibrium divided by the volume. So all these numbers that we have here must all be divided by 5. So if we say 0.68 divided by 5, that will give us 0.136. If we say 0.47 divided by 5, that's 0.094. And then here's 0.2 divided by 5, that's 0.04. Then here's 0.1 divided by divided by 5, that's 0.02, right? So now at this point, we have all our concentrations. So that means we can now calculate our Kc. So to calculate Kc, we need to note Kc is the concentration of the product over the concentration of the reactant. Our product, we have oxygen gas, and then we have to be mindful of the coefficient. It's only 1, so we're going to leave it like that. And then multiplied by the coefficient of HCl gas, and then we can see that the coefficient is 4, which then becomes the exponent over the concentration of the reactants. The reactants are this 2 here. So we will have the chlorine gas, but then chlorine gas has a coefficient of 2, so we need to square here. And then we have H2O steam, also has a coefficient of 2, so we need to square. Now, after this step here, you need to ditch off the square bracket and now start to use round brackets, because now you understand that you are now substituting the values. So this is 0.02 multiplied by 0.04 and then to the exponent of 4 over chlorine gas is 0.094, and then here we have square, and then again 0.136, and then square, right? Okay, so at this point, you need to just punch all of this into your calculator, and then your Kc will be 0.0003 if you just wrote it in normal form. But if you use the scientific form, then you had 3.15 times 10 to the exponent of -4 if you round it off to 2 decimal places. So again, remember, Kc is simply just the ratio of the concentration of the product over the concentration of the reactant. So it has no SI unit. So no SI unit for Kc. And then, okay, so that's how you could have calculated the Kc. So again, all that you needed to note was the fact that the reverse reaction was the one that was being favored. So you needed to add on the reactant side and subtract on the product side. As you can see from that graph, the graph was simply illustrating that the products are now decreasing. If products are decreasing, that means reactants are increasing, because this is a reversible reaction, right? So, okay, let's now proceed. We have 6.3. It says the pressure is now increased. How will this change affect the value of the equilibrium constant? If they're talking about the value of the equilibrium constant, they're talking about the Kc value. How will this affect the Kc value? Now, this is a question that is similar again to that one that I did previously. Note, I made you note this, the Kc value can only be affected by the temperature. So whether you choose to increase the pressure, decrease the pressure, increase the concentration of one of those reactants, or increase the concentration of one of those products, it will not do anything to the Kc value, because the Kc value can only be affected by changing the temperature. So our solution for that one should straightforward be remains the same. Remains the same. And then our reason, we have our reason right there. Kc value can only be affected by the temperature. Then you are done. Okay, so we have a 6.4. It says the reaction is repeated with a catalyst. The reaction is repeated with a catalyst. Draw a potential energy diagram of this reaction and indicate the non-catalyzed reaction B and catalyzed reaction A on the same graph, right? So the potential energy diagram that they're speaking about, we know that it is this one, right? So remember, from here, we have discovered that this reaction is endothermic because enthalpy change was greater than 0. So the graph that we are supposed to draw, if we are saying that this is an endothermic reaction, is obviously ta, and then we have to have this. So in endothermic, this is where the products, the energy of the products will be greater than the energy of the reactants. So we have our reactants here and then our products there, right? So, okay, if we are to say this is the original one here, so we need to label it B because it's the one that is without the catalyst, the non-catalyzed. And then now, if we have to add a catalyst, remember, we know what a catalyst does is simply it provides an alternative pathway of lower activation energy. So what will just happen is that now we will have another graph trailing below there, right? So with a lower activation energy, so note that. And then we want to label this graph A, right? So this indicates that it now has a lower activation energy. Remember, when we are talking about activation energy, we are talking about the energy from the reactants there all the way to the activated complex, right? So if you have to compare the energy, firstly of the one that was uncatalyzed, and then compare it with the one of A now that is catalyzed. So we can see that this is our activation energy, uncatalyzed, and then this is the activation energy at A, catalyzed. So now we can see that our activation energy is low. And then that's how we were supposed to indicate that, right? Okay, so again, let's not forget to label. So this is, remember, cause of reaction. And then normally what we have here is potential energy. And then we can indicate that the potential energy is given in kilojoules, right? So just like that, we have our graph, right? So that's how you were supposed to tackle this question, all for a total of 20 marks. So it was a pretty interesting question there. So make sure that you watch the video as many times as possible and just try to understand the approach that I took into solving that one. But with all that being said, please press the thumbs up button if you've enjoyed the lesson and then you have found it helpful. And if you've been watching the videos and haven't subscribed yet, please hit that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.